Okay, so the first speaker is Shlomo Tauber from Tel Aviv University. We'll talk about the fast coloring oracle for average case hypergraphs.
Yes, hi, thank you. I'm Shlomo. I will talk about the fast coloring oracle. It's a joint work with Cassandra Markussen, Ted Pine, Ronit Rubenfeld, and Asaf Shapira. Okay, so in the paper we talk about average case algorithms, which are algorithms that are designed for input drawn randomly from some natural distribution. It typically parameterized by the input size, and when we analyze the time complexity, we look at the expected running time. We focus on the problem of coloring bipartite hypergraphs. So a bit about hypergraphs. A k-uniform hypergraph is a set of n vertices and a set of edges that are tuples of k vertices. So here in the example, the edges are tuples of 3 vertices. And we will call a k-uniform hypergraph a k-graph. So the example here is a 3 graph, and 2 graphs are just the graphs. We don't know. Okay. We say that a hypergraph is bipartite if we can color its vertices in 2 colors in such a way that every edge has two vertices colored with 2 different colors. So for those edges, this is a legal to coloring. We all know that, relatively speaking, coloring bipartite graphs is an easy problem with linear time solution. Loves famously proved that for k at least 3, deciding whether a k-graph is bipartite is NP hard. And Gawaswamy, Hested, and Sudan proved that for k at least 4, even if we know that the k-graph is bipartite, to find a legal coloring with constant amount of colors that doesn't depend on the hypergraph size is NP hard. So what does it mean coloring average case hypergraphs? We denote as Tn of k to be the set of all labeled bipartite k-graph with n vertices, and we sample uniformly one of them. We want to return a legal 2 coloring, not like approximation or some constant, legal 2 coloring always, and we hope to do so in polynomial time on average. Pearson and Shecht were the first one to address the task. They designed a deterministic algorithm that does so for bipartite 3 graphs and has a polynomial time on average. And recently, actually last year, Lee, Mula, and Nagel extended to all k at least 3. They provided a deterministic O(n) of k algorithm. So our main questions were, Pearson and Shecht, as well as Lee, Mula, and Nagel, used regularity-based techniques, which are very powerful techniques, but leads to a huge constants. We asked whether can we avoid such strong techniques, still remain efficient, and by that get more practical implementation. And still in the same context of average case, if we also get some arbitrary vertex, can we return the color of the vertex in some consistent way, and can we do it efficiently? So for our first task, we answer that yes, there is a deterministic algorithm that still remain efficient, and not using the regularity-based techniques. And if we allowed randomness, we can improve it even more. Our third and main result is the coloring oracle, so we first define it. The coloring oracle is a randomized algorithm that gets bipartite k-graph H, some arbitrary vertex U. It has probe access to the edges of H, and it always returns some color to U, 0 or 1. So it's a bit a simple problem because H is bipartite. For every vertex, there is a legal coloring that color the vertex with the color 1. We can always return 1. So we add some conditions, and we say that for every sequence of queries, the answer of the oracle remain consist with a single legal coloring of H. And it's still not that hard because given H, we can extensively search for some legal 2 coloring, store it in the memory, and in every query, we return the color of the vertex. It has exponential runtime and polynomial space complexity, but it satisfies those conditions. So we also says that the oracle uses only little o of n memory to keep information between queries to still remain consistent. Is there an algorithm that can do so? Can it be efficient? Our main theorem says that there is such an oracle. Its time complexity is constant on average, and it means that in the average case, to color the worst case vertex of the hypergraph is constant. And when we started to work on the oracle, we thought that in the best scenario we will achieve constant memory. Amazingly, we discovered that the oracle doesn't need to share any memory at all and still remain consistent. All of our results depend on the good K-graph property we found. So actually, average case algorithms often rely on some nice property that most instance satisfies. And if instance satisfy that property, it ensures efficient solvability. So what does it mean to be good K-graph? It means that if H is good, we need only constant amount of samples to find a copy of KLL. And what is it, a copy of KLL? It's a bipartite K-graph. It has L vertices in each of the independent sets, and it containing all of the edges that has exactly one vertex from one of them, and the remaining k-1 vertices from the other, as we can see here. And if we choose L appropriately, the copy has a unique two coloring. Being good also means that for every vertex and every copy of KLL, on average, we need constant amount of samples to color the vertex in a unique way by the copy. So what's happened here? We have a copy of KLL and the vertex V here. We know that the copy has a unique two coloring, so we color it. Now we want to color the vertex V according to the copy. So if H is good, we need only constant amount of samples to find k-1 vertices that share an edge with the vertex V. And each one of them share an edge with k-1 vertices in the same independent set of the copy. So now each vertex we sampled must be colored with the same color according to the copy. And to keep the coloring legal, V must be coloring with the opposite one. So if H is good, we really easily find the copy of KLL. And once we found that copy, we can color each vertex by using only local computations. So that's really cool. Our key lemma says that when we sample uniformly bipartite K-graph, we get a good K-graph with overwhelming probability. So we can get to the coloring oracle, and the coloring oracle gets bipartite K-graph H, a vertex U, and it wants to return the color of the vertex U that consists with the lexicographically first legal to coloring of H. We have here an example of bipartite tree graph, the vertex U, and the vertex label as 1, which is going to be important. So suppose H is good. We know that really easily we will find a copy of KLL, and really easily we will color the vertex U according to the copy. The only thing that we want to notice is that anytime we sample the copy, we color it in dependent sets in a consistent way each time. And we want to do it without sharing any memory, but we know we already said that we can do it. So we start to look for a copy of KLL. And we remember that not only U is connected really easily to the copy, also the vertex label as 1, actually all of the vertices. So we look for a copy of KLL, and we also look for k-1 vertices that share an edge with the vertex label as 1. And each one of them must be colored with the same color according to the copy. Once we found one, we have a copy of KLL, and we know how to color it in dependent sets in a consistent way. So if we did find such tuple, we can color U. We can start sample vertices and really easily find k-1 vertices that share an edge with the vertex U and color it in a consistent way by the copy. And if in some step the oracle fails, we just go to step 7 and extensively search for the lexicographically first legal to coloring of H. Okay, so for summary, coloring bipartite K-graph with a constant amount of colors isn't hard. We address the task of doing so in the average case. We provided a deterministic algorithm that doesn't use regularity-based techniques, still remain efficient, And if we allow randomness, we can improve it even more. We introduce a new oracle, a coloring oracle, that's given some arbitrary vertex, color it in a consistent way. It does so in constant amount of time on average, and it doesn't need to share any memory at all. What the oracle reveals is that even though being bipartite is a global property of the hypergraph, in the average case, we can use only local computations and still resolve it in a consistent way. So, thank you.
Thank you. Any,
So it seems like your algorithm is using the random assumptions in very nice ways. But I'm curious if your algorithm can handle a helpful adversary, where let's say you draw a random graph as you want, but the adversary only removes some edges. So for instance, they might remove an edge from every KLL, for instance. So you can't use that anymore, but the coloring problem becomes easier, right? Because some edges have been removed. Can your algorithm handle such instances?
Actually, I think that it can still remain as a unique coloring the copy, even if we remove some edges. Maybe we will need to take a larger constants of we denote L to be 5K. Maybe it needs to be a bit larger, but really depends, I think, on the assumption you take, which edges you remove, how many, and stuff like that.
Yeah, I guess
intuitively,
right. The problem is getting easier, but since you're trying to find these specific structures in the graph, they may not exist, right? The adversary may remove some edges so that none of these structures exist.
Yeah. Okay. So.
But they're always helpful, right? Because they're making the coloring problem easier.
Yeah. I don't know, from now, to answer, sorry.
No, I'm just curious.
Yeah.
How exactly you use the first vertex? I probably didn't understand it well. I mean, you can't keep its color, right, in memory. So what exactly is the role of this vertex?
Okay. So we know that in the lexicographically first legal to coloring, the first vertex is going to be in the independent set that color with the color 0.
Oh, okay.
So we make sure that each time we color the copy, that independent set is going to be colored with the color 0.
Okay. Thank you.
Yeah.
So when you say average, you are saying you draw a graph that is promised to be bipartite, right?
Yeah. It's conditioned to be.
If you just draw a random graph, say a Gaussian E, or just every edge with probability half, can you quickly test whether it's it's bipartite or not?
I think
or
with high probability it won't be bipartite.
Oh.
So we really need to add the conditions.
Okay.
Condition.
Let me just forget my role. It's actually, because we want to do it on average, and it's not only that with high probability it's not going to be one, but it's going to be, the probability is going to be so small that even if you do the exhaustive search on the worst, you'll still be fine.
Oh, I see. Yeah.
Remember you also.
Any more questions?
I remember you also said that regularity lemmas methods are not used. That's a different part of. That's one of the contributions.
Yeah.
I'm curious about what's also the difference between the complexity.
So we in the deterministic algorithm we lose a bit because Lee, Mula, and Nagel, the deterministic algorithm, its running time is O(n) of k, and our is n to the power of O of k. It's still because we don't have the huge constant like tau type constants, so it's a bit more efficient.
Okay, thank you very much.